Okay, should we get started?
Sure.
Okay.
Still hear me?
All right, welcome everyone to today's CDAC webinar. This is the 157th seminar in our series on materials at extremes. And today it's my great pleasure to introduce one of our longstanding close colleagues in CDAC, Dana Dattelbaum from Los Alamos. Dana is an experimental chemist and material scientist and one of the leaders in the field of dynamical properties of materials in general, and in particular soft materials such as organic molecules and energetics and polymers, which she'll tell us about today. And her advances include contributions to shock and detonation physics, developments of equations of state, and shock-driven chemical reactions. Dana obtained her bachelor's from James Madison University and a PhD from the University of North Carolina, both in chemistry, and moving from there to Los Alamos, where she has risen through the ranks to become group leader, program manager, and senior scientist. Dana has received many awards for both her scientific and management accomplishments, including fellowship in the APS, Los Alamos Laboratory Fellow, and DOE Lawrence Award winner. And she's served on numerous committees, including the Scientific Advisory Committee for CDAC for many years. So we're really delighted, Dana, that you were able to take time out of your busy schedule to give us this talk. Over to you.
Great. Thank you, Russ, and thanks for the invitation, and thanks for everyone who's joining today. Russ and I overlapped at the March meeting, and you can see that this is a reprise of that presentation, so I haven't changed the slides at all. And this was an invited talk within the our topical group section. And what I tried to do in this talk, it's a little bit different than the abstract that's published there and even on the CDAC announcement. What I'm going to try to do in this talk is walk through some of the unique features of the dynamic response of polymers. And then at the end, well, throughout the talk, I'll highlight examples of where we are using X-ray light sources to gain more information about what's going on under dynamic loading. And then at the end, I'll talk about some of my recent endeavors, which includes I have a number of students and postdocs associated with working on some SPAL experiments this summer, and we did additional work at APS this past winter and spring. So I'll go ahead and get started. Obviously, I'm not the only one that has worked on this. I have a large team of collaborators at Los Alamos, which is one of the great things about working at the national labs. So I list a number of my co-authors here and collaborators at the top. I also want to recognize the facilities that this work was done at. So it was done at our two-stage gas gun at Chamber 9, our high-performance gun at the DOS building, and then certainly the dynamic compression sector and the teams associated with those facilities for supporting the experiments. And most of the work was supported by the Dynamic Materials Properties Program under NNSA. So I thought I would just start out with a very high-level introduction about why are we interested in the high strain rate and shock behavior of polymers. So if you look at kind of the applications of polymers, they range, you know, they're in all the materials that we use, right? They're pervasive, right? But why are we interested in the high strain rate and shock behavior? So you can look at things like vehicles and automobile, crashes and protection of people within automobiles. So a lot of times, those reach strain rates of about 10 to the third, 10 to the fourth per second, and you may want to take advantage of some of the features of polymers in protecting, inhabitants of a car, right? Another kind of good one to show is I show NASA Artemis on the side here. Also in the space program, lots of polymers that are potentially subjected to extreme conditions and extreme environments during launch and reentry, but also there's, think about the field of protecting spacecraft with high velocity impacts in space. And so in fact, many years ago, we were contacted by some NASA colleagues due to our capabilities to look at very high velocity impact into polymer foams that originally that was going to be part of the Artemis mission, where polymer foams are part of the protection of the capsule, and these impacts were on the order of 14 kilometers per second. So that kind of gives you a range of like sort of the span that we might be doing impacts on the order of several hundred meters a second to kilometers per second. So what I show along the bottom here are just a couple of microstructures. So a lot of what we're asked to look at are, just base polymers of different structures, composites. So we've done a lot of work on carbon fiber filled and glass filled and polymer filled polymer composites. I show here some structural foams. Foams are often used in these applications as sort of centering materials or positioning materials, structural supports. And then over here, I'll rerun this movie. We had an LDRD project a few years ago, actually designing the properties into the material. So this is an example of a fractal polymer structure that we 3D printed using 2-photon polymerization. And using this fractal structure, we're able, and I referred to these in my paper as interface dominated materials. We showed that we could reduce the shock going through the material by 10-fold over just a millimeter or two in the material. So these are also potentially applicable to the warfighter in terms of helmet materials, and these were in particular looking at vehicle protection. So in general, there are a lot of interest in polymers. I think they've been kind of understudied as a whole as far as materials classes. And so what I want to do today is kind of talk about what are some of the unique features that polymers exhibit as they're undergoing high strain rate and shock loading. And then I'm just going to kind of break it down by property and regime of where you're studying the material. And it's really just designed to give an education of things to keep in mind and be aware of, and what are some of the differences you need to capture when you're modeling these materials under these conditions. So this first slide, I just kind of, this is actually borrowed from a colleague of mine from several years ago when we had a program on this, just highlighting some of the differences of the dynamic responses of polymers compared to metals. And if you go over here to the polymer side, what you'll see is that, the moduli and the strength are strongly dependent on the loading rate as well as the temperature compared to metals. Much stronger rate dependence with viscoelasticity. Also, polymers are often multi-phase, so they typically could have amorphous and crystalline domains as well as fillers within them. And so we have to capture those different domains because those domains dominate the properties. So for example, the amorphous domains and crystalline domains can lead to, different viscoelastic properties above and below the glass transition, and also crystalline phase transitions that are only within a portion of the polymer network. Going down to bullet number 3, within EOS, of course, you're going to have potentially solid-solid transitions associated with crystalline domains. You could have solid, liquid, or solid, above TG transitions, glass transitions, but also because they're organic materials, and I'll touch on this, they also, when you hit a certain temperature in the dynamic loading, they undergo decomposition chemistry, much like explosives. If you look at their damage responses, they damage by different mechanisms than metals. They damage by a number of different mechanisms: viscoelastic, brittle, ductile, and crazing failure modes. That's something I'll talk about at the end that we're trying to get real-time data on as far as ball failure. And then as far as the EOS development, we could potentially treat a lot of materials as being in equilibrium in terms of their EOS. But when we are developing equations of state, particularly at these lower rates, we incorporate a deviatoric component, which is basically always in non-equilibrium, and that deviatoric component is based on viscoelasticity. So I just wanted to point out some of those differences in a single slide. And then there's a good review article on this by Clive Sivor and Jen Jordan, just talking about some of the strain rate regimes and what are some of the properties of polymers you observe in these different strain rate regimes. So historically, there's been a fair bit of shock data reported, both in the Los Alamos and Livermore shock compendia, as well as there's a lot of work done in Russia in like the 1960s to 1980s timeframe. And in that time frame, a lot of the experiments used plane wave lenses to drive flyer plates, which would then impact a plate. I don't know if you can see my mouse, but it would impact a drive plate, and you'd have a number of samples on top of that. So instead of using guns, we used to use explosives to drive shocks into polymers. And so the majority of our historical data comes from these types of techniques. And it was recognized by several folks that when you looked at polymers, there was like universally a couple features. I'll go into them in more detail. But that you would see, and I just plot here in shock velocity, particle velocity plane, a number of different Hugonios for different polymers. They're offset in shock velocity, just for clarity. But what you'll see is that a number of them have like cusps and kinks and nonlinearities associated with the material as you go up to higher pressure with the Hugonio. And later, colleagues of mine here at Los Alamos published a report based on Bill Carter and Stan Marsh's work in 1995 that basically described the threshold for these cusps in these different polymers and what the volume change across the cusp was. And that those cusps were attributed to dissociation of the polymer or decomposition into small molecule products. And what you see is that most of the polymers have a cusp in the regime where the particle velocity is between 2.5 and 3.5 kilometers a second, which is equivalent to a pressure threshold starting sort of around 20 GPa. And for some materials where there's not a very large cusp such as PTFE, it's been estimated at like 41 GPa. So somewhere in that 20 to 40 GPa, you would expect that your polymer is no longer a polymer, and in fact, it's a product gas, a solid gas fluid mixture that much like an explosive, and the volume change across those transitions has a lot to do with the polymer structure and the side chain groups. Today we do a lot of experiments with either gas gun drive or laser drive, and so our diagnostics are far better as far as measurement of the the wave going into the material and the shock waves coming out of the material. And we can do a whole variety of different experiments, such as shock release experiments or even embedded gauge experiments, where we can follow the flow, the shock-driven flow, as a function of time and position. So I just show a picture here of our two-stage gas gun at Los Alamos. It's a large bore two-stage, and we are able to do a variety of different experimental geometries to study polymers. So typically we employ a front surface impact geometry where we might impact the polymer into a window. That's kind of our easiest experiment for getting a Hugonio state. And you can also get some temporal information from the wave profile at the interface. We do a lot of transmission experiments where we launch an impactor into a drive plate, much like you saw in the plane wave lens experiments. And then we observe the shock wave going through the sample, again, typically at a windowed interface. And so we can see how that wave evolves over time and distance. And then lastly, one of the unique diagnostics we have here at LANL is embedded gauge techniques, which we apply to polymers because they're non-magnetic. And so this is based on electromagnetic gauging. And so we can then observe the evolution of the shock wave as it travels into the materials. So I'll be showing some examples of data from these types of experimental techniques. And of course, obviously, there are laser drive techniques, which we also employ. We haven't done as much in the polymer area using laser drive techniques, but certainly other groups have. I want to give a little bit of discussion about how these features that I mentioned at the beginning give rise to evolution of shockwave profiles. And so you end up getting, anytime you have a volume discontinuity or some sort of evolution due to viscoelasticity, you end up getting wave evolution. And so this really is just to point out that the propagated shock waves give you a lot of information about timescales, volume changes across transitions, and kinetics. So I show this for a phase transition. This would be a densification transition. So the diagram on the left is pressure-specific volume. You've got here a Hugonio for the first state, and then you've got a Hugonio associated with the second state. And this could either be a solid-solid phase transition, or it could be a densification transition, such as decomposition. But as you shock into this manifold of states, you're going to get a variety of different profiles. So if you shock just in a phase space where you're only accessing the first state, you would get a single wave. But as you get into this regime where you start to see these evolutions between structures, you start to get these multi-wave structures. And so these are similar in many ways to detonation waves, but they're associated with densification transitions instead of expansion or volume expanding transitions. So you can see that you'll sometimes see evidence of a first wave followed by a second wave that could travel slower. Usually it could travel slower than the first wave, or eventually catch the first wave. And then often some of these rounding and second wave features are associated with kinetics of the transition. So I just wanted to put this up here to just say that when we look at the shock waves coming from our polymer samples, we have to keep in mind there's a lot going on here, and we can use the shock wave dynamics and carefully design our experiments to get at some of that quantitative information just from the profiles themselves. So I'm going to use polyethylene as an example today. And Los Alamos has studied polyethylene for over a decade now. We used to have a fairly large project on it, both for DOE or NDOD interests. And I want to highlight some of these features using polyethylene as an example. So the two types of polyethylene that I'm going to focus on today are high density polyethylene, which is like a typical milk bottle, The thing that is associated, I want you just to remember about high density polyethylene is that the reason it's high density is because it's highly crystalline. So the material that we studied was nearly 80% crystalline. So if you think about the spaghetti structure, that almost 80% of the material is organized into these crystalline domains that have order associated with them. And the reason that they can do that ordering is that the molecular weight is not very high. It's about 300,000 in this case, for the material we studied. The other type of polymer, polyethylene, is ultra-high molecular weight polyethylene. That has been found a lot of uses in armor and protection and protective equipment because it tends to have some texture associated with it, and the high molecular weight inhibits crystallization. So we're typically at around 50% crystalline, and also because of that, we end up having a lower density in the final product. So I just want to introduce you to those two materials. The other thing I'll just point out is that if you look down at the lower left corner, you can see the DSC traces with in this case, the exotherms are up, so endotherms down. You can see the much larger melt transition associated with high density polyethylene versus ultra high molecular weight. And then again, if you look at just the DSC traces, you can also see they both have glass transitions around minus 35 degrees. Okay, so I want to break this down kind of by regime, and I'll use this plot to walk through the rest of my presentation. So I introduced Hugonio data in the shock velocity, particle velocity plane, talking to the historical data. So I've selected two polymers to plot in this figure. So this is the Hugonio data for a polyethylene in red, and then polystyrene in blue. So if you go back to this Carter and Marsh publication, the two things they discuss in detail is that cusp that I already talked about, and then also the fact that at low pressures, unlike metals, the Hugonio data does not extrapolate to the sound speed in the material. So first I'm going to talk about the low pressure response of the polymers. So what you can see here is that polyethylene in the red looks pretty linear in this plane, whereas polystyrene has that cusp associated with it. And, in fact, we do not extrapolate to the bulk sound speed. And so at first, the first thing I want to point out is that at low pressures, that's the region where you would expect different compressibility of the different domains in the polymer, and as well as viscoelastic effects to be dominant. So you end up having curvature at low particle velocities in this plane. That's associated with compression of the free volume in the network. And then you're going to have viscoelasticity because commonly you're in the 10 to the 4th to 10 to the 5th strain rates in this regime. And my little spaghetti diagrams are shown at the bottom. So if you think about compressing these structures, think about I show here schematically like the crystalline domains by the ordered sections, and then the spaghetti linking them all is the amorphous domains. So a big question we had was, when you compress this structure, how is that compression energy distributed between those two different domains? Like, I mean, you might expect that the amorphous domain would take up, and you'd see a lot of the free volume associated with that compressing out first. And when thinking of it from the high pressure community and the diamond anvil cell community, you might actually think that the amorphous domains might act like a hydrostatic medium around the crystalline domains. And some other things that could happen in this regime is you could drive solid-solid phase transitions. We know that phase transitions for crystalline materials tend to be quite rich at low pressures. With polyethylene, there's also, I showed you the melt temperature. There's also the question of, do the crystalline domains melt under shock loading, and can you see evidence of that? Because the expected change in volume associated with melt in polyethylene is on the order of 20%. And then, of course, like you might expect there might be some chain orientation or texturing that could take place within these structures. So we performed a number of shock experiments on those two different types of polyethylenes, and I show that over on the left-hand side overlapped with the Marsh data from the Marsh compendium. And what I want to show you is just that if you zoom in on this low pressure regime, there looks like what could be like a lot of scatter in the data. But when you actually separate it by material, what you see is that the higher density polyethylene, the HDPE, lies higher in the USUP plane, means it's less compressible than ultra high molecular weight. And almost universally, there's this cusp down here, which we believe is associated with a solid-solid phase transition. And that cusp, the magnitude of that cusp is strongly related to the amount of crystallinity in the polymer. So there's, this cusp is at about 0.15 kilometers a second or 150 meters a second. And again, you don't extrapolate to the sound speed because you are compressing out a portion of that free volume associated with the amorphous domains. So what does this look like in the wave profiles? So on the right-hand side, I show some of our embedded gauge measurements. So we basically measure the shock wave profile at the impact interface and then at a variety of depths into the material. And I believe this one is for high density polyethylene. Sorry, the zoom window is covering part of my my PowerPoint slide. But what I wanted to show you here is that over time and distance, that initial wave in the material, which looks very much like a very clean, sharp, flat top shock wave, evolves into this rounded structure. The first thing is that this rounding and this evolution of this structure has been known to be or proposed to be related to viscoelasticity. And you can think of this kind of like silly putty. If you smack it really hard, it's going to, it's going to respond with a stiff response. But over time, it relaxes. And so that's what's actually happening under shock loading. So you shock it, and then the material relaxes. And as it relaxes, you can see the evolution in the wave profile. And the rounding is the signature of that relaxation. So the relaxation has a time associated with it that, and when you look at this in a pressure particle velocity plane, you basically shock up to an instantaneous state. So it's an instantaneous Hugonio state, and then you relax down to higher particle velocity in the equilibrium state. So just from the wave profile, we get a measure of the instantaneous state and then the equilibrium state and the time, the relaxation time associated with, converting, that relaxation process. And the way we've been modeling this at LANL is that we have developed something called a gap model or a glassy amorphous polymer model that Brad Clements developed. And with that model, again, I pointed this out earlier, he has both a volumetric or essentially EOS term, but also a deviatoric term in order to capture that. And he captures that through a Prony series expansion of Maxwell elements, which is a common approach for viscoelastic materials. One of the things I will note is that that two-wave structure associated with viscoelasticity is basically overdriven by about 4 GPa or 40 kilobar. So what that tells us is that the viscoelasticity really dominates at these semi-low strain rates, still 10 to the fourth, 10 to the fifth per second, but lower pressures. And the relaxation time can be somewhat significant. So I guess in my view, just a commentary is that much of the Hugonio data for polymers at low pressure in the literature is incorrect in the sense that it's reported as a single wave structure, and you don't really know if people, because of the measurement technique and how they've analyzed the data, if they've reported the equilibrium or instantaneous states. So that's one thing on my to-do list working with my students is to put out a paper on viscoelastic relaxation times as a function and actually do the formal analysis, reanalysis of some polymers in this regime. I mentioned that we have a glaciomorphous polymer model that we're using at Los Alamos. It's been implemented into Abacus, and then it's been implemented into CTH. But as I mentioned, that model basically is broken into two components. It has an equilibrium portion, which is volumetric. It's actually somewhat based on in our case you're using like a very simple form. It could be a Meagren-Heisen form, or in our case we use one of the forms that's used for polymers, a Tate equation of state. And then there's a non-equilibrium form, which is related to the Maxwell elements. And so we parameterize this model based on quasi-static data as well as thermal expansion data, stress strain data to get the deviatoric components, and then we can then use that to simulate the shockwave profiles. And I think I show an example later on, but it's that deviatoric component that allows us to capture that rounding in the wave profiles. The next thing I wanted to point out is as we all work in high pressure science, like we know that often there can be a lot of phase transitions at low pressures. And most polymers have pretty low symmetry structures as far as their initial crystalline structure. So they're often orthorhombic or monoclinic structures. And one of the things that we saw in our wave profiles with HDPE, so the highly crystalline form of polyethylene, is that over time and distance, we actually saw that wave split into what looks to be a three-wave structure. And those transitions, those waves, are related to crystalline phase transitions. So they overlap, fairly well with what's been measured in diamond anvil cells. There's a group in Italy that did a lot of work on polyethylene. But it's associated with these transitions between the monoclinic and orthorhombic structures. And what we saw is and that's associated with that cusp at about 0.15 kilometers a second or 0.4 GPa, and that multi-wave structure is more pronounced in HDPE versus the ultra-high molecular weight because it has a higher percent crystallinity. So the only way we can really detect this is by running the wave and looking at the wave over time and distance. And it turns out these transitions also occur quite sluggishly, like it takes almost 4 millimeters for that multi-wave structure to develop in the material. And at least at Lanol, and I don't believe anywhere else, there's been no attempt to model that yet in a multi-phase equation state framework. One of the things that we wanted to do was actually look at some of these phase transitions using X-ray diffraction at the dynamic compression sectors. This is work that in collaboration with Rachel Huber at Los Alamos. So with the coming online of DCS, we could get real-time time-resolved X-ray diffraction of our polymer as we were shocking it. And so what is shown here are some of the detector images of polyethylene shocked to different conditions. And then I show the diffraction patterns down on the lower right. And basically, so this one, the first figure, figure A, just shows at the time we had 4 cameras. This was some of the early work at DCS. We had 4 cameras taking 4 images. And what you can see is that there is, in fact, an evolution of the wave in time as you go through the sample, or evolution of the diffraction pattern as the wave goes through the sample to a depth of about 2 millimeters. And then if you look just at the images on the detector, what you can see is that there is evidence of orientation, because you see that intensity kind of along the x-axis here. You can see that intensity change, which indicates that that shock compression is driving orientation of the polymers, specifically of the crystalline phases, the crystalline domains under shock, which is interesting because they're highly, orienting to the shock direction, but then it's also driving this phase change. So again, we see the growth of this monoclinic structure and the disappearance of the orthorhombic structure as we shock to higher pressures. So that was very satisfying. That's, I believe, some of the first measurements of their kind to be able to observe these phase transitions in the crystalline domains within the polymers, especially because they're low Z materials, and those crystalline domains are only a portion of the structure. And I will say, I think the only way that this has been possible is by using third generation and now fourth generation light sources. The other thing that we did is we eventually started shocking. So we shocked within those phase transitions. So we also tried to address the question of, okay, we have Hugoniot measurements of the bulk polymer, and now we have the diffraction measurements that just look at the crystalline domains. And so we can actually look at, and this is something we describe in detail in the paper, is that we can look at that partitioning of compression energy between the crystalline and amorphous domains, because we can use the diffraction compared to the bulk material, under shock. So that's something we discussed in the paper, but it is, we do see that there's more compression of the amorphous polyethylene compared to the crystalline polyethylene, much like we would expect. And I'd say the next thing we need to do is do this as a function of strain rate. So we do have some of the data collected where we've done dynamic DAC experiments, and I'd like to tie all that data together as a function of strain rate. Okay, so now I'm going to focus on the high pressure regime and talk a little bit about dissociation. So again, I have polyethylene in red, polystyrene in the blue, and I think my chemical structure for polystyrene disappeared. I was thinking maybe it would come back. Anyway, so polystyrene has an appended benzene ring or phenyl ring. And so what you can see is that there's this large cusp in the Hugoniot. And again, that was, proposed to be related to dissociation. And when you look at that in the pressure volume plane, it's a densification transition. And usually it occurs around 20 GPa. And we expect that above that transition, we would form products much like you have in high explosives, so solid carbon, different fluid mixtures, like based on the polymer structure. So that could include water, ammonia, things like that, methane. And one thing to note about this is that it's irreversible. So as a chemist, you know this, right? But when you think about the shock physics related to this, let's say you shock above this transition, and you were to send a release wave through the material or a second shock, your wave speeds are going to be incorrect unless you measure this, unless you model this irreversible chemical dissociation. So
Could
at
I
Los
ask
Alamos, yeah.
Are you at any point, say, during the shock, forming graphitic sort of structures, or if you go
Yep.
to high pressures, are you going to like a diamond-like structure?
Yeah. So the way that we model it currently in our codes, which is too simplistic, is that if we're above 25 GPa, then we assume that all the carbon goes into the diamond phase. We've already shown with some of our light source experiments that that's not the case, right? It turns out to be a mixture. And what's very nice about again, the third and fourth generation light sources is that you can go in and you can actually measure things like, get at the density of the particles, even with SACs, with the SACs contrast, but you can also potentially get the XRD information about the material. And what we're finding is that it's not as simple as just graphite or diamond, but that's the way we model it. If we're under 20 GPa, at the low pressures, we model it as graphite. If we're above 20 GPa, we model it as diamond. And I think over time, our models are going to evolve. But those structures that are formed in the carbon are quite complex. In fact, in many cases, they probably have other atoms entrained within them. We've seen this in benzene, where we saw hydrogen entrained in the layered structures. And then with these materials, I would expect nitrogen and other elements to be entrained within the carbon. So they're not simple structures by any means. Definitely
Thank
an
you.
area for investigation. Yeah.
If I could ask
So, yeah.
one more question. So when I think
hmm
of the cusp and the reform, as a materials chemist, I'm thinking of breaking of some bonds, covalent bonds, at
hmm
the place of the cusp, and then reforming of new covalent bonds. Can we think of it
Yep.
that way?
Yes, absolutely. And in fact, we have done some related experiments again at light sources looking at products, and it turns out that those bonds may be formed, and when you release it from the shock state, as you release it, there actually could be a freezing temperature where you basically freeze out chemistry. So we've seen that as carbon clusters grow, there's a freezing temperature as you release it from the shock state. And if you get below that freezing temperature, you essentially lock in the chemistry, or you lock in the cluster size. So there's so much rich work that can be done in this area. It's hardly known, what's going on. So we're
Sure.
trying to make a dent in it, but yeah, there's a lot to be learned in this area.
Thank you. Thank you.
Um,
Interesting.
sure. Yeah, so I'll just point out, we've probed above that cusp for both high density polyethylene and ultra high molecular weight polyethylene. And one of the new techniques that we did to do this was we performed some shock release experiments at very high pressure so we could get sound speed. But we have developed these new equations of state. So the historical equation of state is Sesame 71, 73. Now we have a reactant and product equation of state, with the reactant being the one in black and the product being the one in the gray. So what that allows it to do, our codes to do, is essentially we can switch now between a reactant equation state and a product equation state. And once we're on the product equation state, you don't you don't go back on the reactant equation state. So it captures this irreversible chemistry, which is not what was done historically. And then we use a code, a thermochemical code called Magpie, which is very similar to Cheetah. And that basically here, like I mentioned, it models the products of polyethylene to be diamond, methane, hydrogen, and essentially dissociated hydrogen protons or whatever. So, but you can see over time at various pressures the products, as you overdrive that cusp, what you would expect that product mixture to be as a function of the pressure, which also gives you what the temperature would be. So we are modeling that with a very simplistic thermochemical code based on equilibrium products. I think I'll skip over this one, but just to say that we did experimental techniques to validate those product equation of state by essentially measuring the sound speed at pressure after we've already shocked it into that product regime. And I think the exciting part here, and this B figure is missing, I can't see it, but what you can see we took this also to APS and DCS, and if you shock above that cusp, we actually saw the disappearance of the polyethylene peaks. And in some cases, we've seen the appearance of peaks associated with like graphitic phases if we're, at different various pressure regimes. But we do see the disappearance of the polyethylene diffraction once we get above that cusp. Okay, so now I want to just pivot for the last portion of my talk and talk a little bit about damage. So in a lot of applications, these polymers are subjected to impact loading. And of course, whenever we're shocking and releasing the material under impact loading, you need to think about SPAL, which is basically putting the material into dynamic tension and looking at how polymers actually fail compared to metals. There's been a lot of work as far as how metals fail, but very little work as far as the mechanisms of how polymers fail. So we know there's historical literature looking at glassy polymers where samples were recovered after spalling them under using shock and release. And what they've noted was that these are for glassy amorphous polymers such as PMMA, polycarbonate, and epoxy. The spall strengths are quite low, so it's pretty easy to observe as far as like the shock condition. to observe damage in the material. And you can see this is work on PMMA and also polycarbonate. They have very brittle crack-like behavior. But then there are a lot of other polymers where we just have shock wave profiles and not any recovery work. And it's like there's a big question about what is happening in these materials, right? So you don't see a pullback signature, you just see this kind of drawing, what looks like drawing behavior. So you don't, when you see the release, you don't see a pullback that would indicate that you have shock reverberation in a like scab, like you would see in a brittle failure mechanism. So we do these experiments in a symmetric impact configuration. We use a polyethylene impactor impacting a polyethylene target. Just for time, to make sure we have time for questions, I'm going to go kind of quick through this. But we did spall of high density polyethylene at a variety of conditions. And again, this is what the wave profiles look like, where you don't see that reverberation at high velocities. You just sort of see this drawing. You don't see any waves reverberating in the material. And you might see something when you go down to lower velocity, some evidence of a pullback signature. And our initial modeling of this several years ago was using that gap model, but adding a crack model into it to capture failure. But we know that this is not brittle behavior, but we still used a crack model that it was developed by John Dienis many years ago at Los Alamos that formed the basis for viscosgram. And I just want to point out what we're doing now, which is over the last few months, we've observed in situ spall the damage of the polymers in situ using X-ray phase contrast imaging, again, at the APS, at the dynamic compression sector. And I believe it's the first time that we've ever observed this and done a scientific study as far as what does the damage look like in real time. So in these experiments, again, you're bringing X-rays from the synchrotron, you're passing them through your material to a scintillator, and then you have intensified CCD cameras, and now we can take up to 16 frames during a single shock event. Orthogonal to that, you're using a gas gun to launch your projectile into your target. In this case, this is a foam target, but we are actually launching polymer impactors into our polymer sample. And then we watch in real time the spall damage forming. And I'm going to just hopefully run a couple of these movies. And I don't know if I can step through this actually slowly because of where the zoom. Let me see if I can move the zoom window without disconnecting you. Okay, so I want to step through this a little bit more slowly by frame. So this is one of the polymers that we've now shocked. The shock wave has actually gone through the sample. And if you look, like in this frame, you start to see that evidence of the damage forming in the material. It's very difficult you can see it by eye, it's very difficult to threshold and detect. And then what you see is over time, it just ductily draws. And so you get this very wide damage plane in the material, and then it basically just draws that whole plane apart. So it's quite a large damage plane. And if you go up to higher velocities, the whole polymer basically falls apart like that. So I think this is what we're working on right now. We have a series of recovery experiments planned, and we're looking at 4 different polymers. We're looking at polycarbonate, and then our polyethylenes, and then we're also looking at polypropylene, which has a side chain group on it, but still a very simple structure. If I can get it to advance now. Okay, so I think this concludes my presentation. I hope that I've shown that there are very unique responses of polymers under shockwave loading, and when you observe the shockwave, that the shockwaves that are transmitted through the material, they can be quite complex, and you kind of have to have an understanding of both the chemistry as well as the high pressure behavior of these materials to really unravel what's going on. There's a lot of the details are really not studied compared to other classes of materials. And there are lots of opportunities, I'd say, for research for improving our predictive models, or even developing model forms. And then, as I hope I've shown, bringing high brilliance X-ray light sources to bear on this problem provides new insights into a lot of these phenomena, including phase transitions, dissociation, and damage mechanisms under shock loading. All right, and I'll thank you for your attention today.
Thanks very much, Dana, for an excellent talk. Uh,
Thank you.
the talk is now open for questions and comments. Just unmute yourself or speak up, use the chat. Maybe I'll start by asking, going back to the previous slide, those experiments at DCS are very impressive. I'm wondering, what is the dimension of that image?
Oh.
And what is the overall
Yeah.
sample size?
So the overall sample size is, so the gun there, we're using a 12, basically like a half-inch bore. So the sample itself and the impactor are half-inch diameter. And then what we're doing is only looking at a very small portion in the center of the sample. So, and actually, we do wave code calculations, and we have to position the sample knowing that we're essentially, I guess, making, I think we're, you basically have to do a transition between Eulerian and Lagrangian coordinates to make sure that you can catch the image, because the damage plane, because the damage plane essentially moves through your field of view during the experiment because it's moving at the particle velocity of the material. So this field of view here, and as we're getting it ready for publication, we'll have all the scale bars on it, but essentially we have 1 to 2 micron spatial resolution, and the field of view ranges from 1.3 to 1.7 millimeters over in that frame. So basically we're looking at a very detailed view in the middle of a much larger sample. So we design our shockwave experiment such that it's one-dimensional and we don't have any interference from release waves. And then, but then we look at the center of the sample over about just under 2 millimeters.
Okay, great, thank you. More questions, comments?
Yes, Dana, thank you very much for the talk. This is Steve Gramps from UIC. Can you hear me?
Yes.
Okay.
Yeah, hi.
You mentioned the partitioning of compression between your amorphous phases and your crystalline phases. Can you further quantify that with your measurements? I mean,
Yeah,
you
so
mentioned that
I
there's
would,
more compression in the amorphous phase, right?
yeah, so what we basically did is a very simple way of analyzing this, where we basically, from the diffraction data, we can get, and knowing the crystal structure and the fate, of the material, we can calculate the volume of the crystalline domains as a function of the shock input pressure. So essentially, we get a Hugonio from the diffraction of just the crystalline domains. And then from the bulk, we get the bulk, densification or volume as a function of the shock input pressure. So we just did a subtraction to estimate what the amorphous domains were experiencing. I will say that is simplified for several reasons. One is that there's texture that we're really not accounting for. And the second is that it's not just as simple, for polymer chemists, it's not just as simple as amorphous and crystalline. There's also rigid amorphous domains that transition between the amorphous and crystalline domains. So, but from a simplified view, I mean, you can think about if you have two-phase materials, you could, by doing bulk measurements and looking at the diffracting portion of it, you could actually get the response of both domains. The thing that would also be great is if we could eventually use small angle X-ray scattering to get at the amorphous domains. We've done that a lot for, the products as I showed, but we have not looked at that as far as what we can get from the small angle X-ray scattering for the amorphous domains. And right now, I would probably say that DCS is a bit light starved as far as the SACS data, but on the polymer, but that's something we haven't even tried yet.
Great, thank you.
Sure.
Yeah, following up, you mentioned several times fourth generation light sources, and that usually means free electron laser sources. So have any experiments been done at an XFL like this or on these problems? I mean, to get at the point you just
Yes.
made regarding some of these storage ring sources, maybe LightStar, for these kinds of experiments.
Yes. So we've done our own work on carbon form benzene. We published a paper on benzene, and that's what I referred to when we started essentially with amorphous material, liquid, and we were able to shock it above that transition regime and get diffraction actually from the products. And so that's where we saw these graphene-like structures forming from benzene. But the other group, there's another group out of Germany, and as well as Livermore, have looked at some polymers, quite a bit of polymers at LCLS, because they're used as often as like ablators, and they're used in inertial confinement fusion or IFE type experiments. And so they haven't really focused on getting at the details of the polymer chemistry, but they have started to try to identify what are some of the products or what are some of the changes and could be some of the carbon forms that are forming from polymers, largely though at very high pressures, relevant to like NIF and other IFE type experiments.
Right. Okay, thanks. Roma, I say you have a question.
Hi, hi Dana, really interesting work.
Thanks.
I was wondering about the complexity, I guess, that modelers need to deal with when dealing with amorphous materials. I expect that, working with crystals is a little bit more predictable because you have some kind of periodic behavior, but I guess I'm curious about the complexity there with the modeling.
Yeah, so I would say that one of the things that we don't have a lot of within the lab is, so there are efforts that try to do, million atom simulations and molecular dynamics of polymers. I'd say that has advanced, and certainly different labs have different, have efforts in that. I think the challenge of like trying to, model like different phases, I haven't seen huge amount of progress on that. I mean, I'd have to like do more of a more recent literature survey, because I know one of the problems has always been like, they may model like chains, but you may not be able to get the full molecular weight, right? Or people have like Kyle Cochran and folks at Sandia have done short chains, looking, at a portion of a chain, and try to get like information on equation of state from that, from simulations. But one of the things that's really challenging is trying to build in that crystalline anamorphous structure, and that I'm not sure has been done. The thing I would just say for us is that I think all that type of work is useful, very useful, especially in the sense of like designing and understanding the properties of the polymers. But ultimately, our application, we want to have continuum models that reflect the behavior. And so, what I've just talked about today kind of helps address like what kind of modeling needs you would have to have in different regimes. Like for instance, you probably should capture this viscoelastic response. Ultimately, I think if the volume change is large enough, you should probably capture the crystalline transitions associated with the polymers. And something that we really have not explored very well is really how much do those change as a function of manufacturing and the percent crystallinity. Because how you manufacture, like polymers, I mean, you change the temperature and then you change the crystallinity.
Right.
Or if you store it at a different temperature, so it's really complicated.
Right.
So I would say from our standpoint, the transitions that we're mostly concerned about is that dissociation, and then at low pressures, capturing that curvature and viscoelasticity.
Yeah. Awesome. Great. Thank you so much.
Thanks.
It seems to me there are some parallels to protein folding. So what you need ultimately is something like an alpha fold for polyethylene.
Yeah.
But that would require lots and lots of data to train on, structural data to develop an alpha fold equivalent. Okay, Kevin, go ahead.
Yeah, hi Dana. My name is Kevin Long at Sandia National Labs. So I'm a little bit familiar with the general amorphous polymer model. Bob Chambers and Doug Adolph at Sandia had put together maybe 15 years earlier a comparable model that's our sort of workhorse nonlinear viscoelastic model. And we've had a lot of success with it, but we also are silent on incorporating phase transformations. For example, crystalline melting in this case at low pressures. I wondered if, so this is kind of a follow-on to Roma's question, but at the continuum scale, like, do you think are you guys on track to, I guess, parsing out that contribution, separating the contribution of viscoelastic relaxation in the amorphous phases versus the phase transformation that's occurring in the crystalline phases in terms of that the low pressure shock behavior? Because I'm having a hard time in my mind figuring out which one we would want to focus on, right? Or how to decide which one is dominant in the data.
Yeah, it seems to me that basically that the viscoelasticity and the free volume compression, just that results in shock heating, and that's the dominant one. As I showed you, like, even if the crystalline domains give phase changes, you have to kind of run the shocks fairly long distance because in order to get them to separate. And it seems like those volume changes are fairly small. So I think it would be just a perturbation in a continuum model. Like if you were to try to model this with a multi-phase EOS, I don't know that it's, I mean, this is actually one of the, there's only a few polymers we've actually observed something like this in. The other one we've certainly seen it in is Teflon. We know there's a cusp there that's associated with those crystalline domains, but again, they're pretty small perturbations, and generally, like, certainly within DOE, we are shocking well above them, so we're like overdriving them. But if you get, so I'm not aware of anyone trying to combine, a multi-phase framework, solid-solid transitions, or solid to liquid, whatever liquid, even if you call liquid in a polymer, right? And I'm not aware that no one's doing that as far as I know here at LANL. And I think it comes down to like the prioritization. I mean, I think some of our other materials just get a lot more attention, and probably for good reason. But I'd say the viscoelasticity and free volume collapse are the things that I'd focus more on, because those can lead to the temperature rise, especially when you have the free volume. You get to much higher temperatures.
Yeah.
And once you get to the temperature that's associated with dissociation, then you need to worry about that you're no longer on a reactance, Hugonio, and so you need to model that as a fluid mixture. So, but I think there's, again, lots of work that could be done in this area. And it was pretty exciting, because even in Teflon, I'd have to go back and look at our data, but I don't think we even saw the phase transition in Teflon, and we went through great lengths to try to increase the crystallinity. And it's only when we got into polyethylene with these high crystalline contents that we actually saw those transitions. So
excellent answer. Thank you.
Yeah. Thanks.
Thanks very much. Any more questions or comments? Okay, well, we're at the top of the hour, so join me in thanking Dana for an excellent talk, and we'll see you next time.
All right. Thank you. Thanks, Russ. See you soon.
See you later.